Thank you for joining us for Smart Construction, Digital Twins for Civil Construction with the Cesium 3D Viewer. My name is Gregory Deal. I'm a full-stack developer with EARTHBRAIN. EARTHBRAIN is a startup founded in 2021. It's a joint venture between 4 companies, Komatsu, NTT Docomo, Sony, and NRI. And the goal of EARTHBRAIN is to provide smart construction solutions to optimize construction processes. If you saw Igawa-san's presentation earlier, he did a very good explanation of smart construction, but just to recap, the goal is digital transformation, which is achieved through software solutions in 3 key areas. So that's optimization of job site construction machinery, data collection, visualization and analysis, and project planning. Today we're doing a bit of a lightning talk focused on smart construction, so you'll hear from myself and 3 colleagues. We will give you a run-through of 2 applications. Smart Construction Dashboard is in that data visualization and analysis category. Simulation is a powerful project planning tool. After that, we will give you a technical walkthrough of our 3D pipeline to process customer data into 3D tiles for Cesium viewers. And then finally, we are going to introduce a new 3D model placement library that is planned for open source release. So Smart Construction Dashboard allows users to create a virtual representation or digital twin of their job sites. This allows them to measure earthworks quantities, track progress, and share progress, and also view conditions without having to visit the site. So typical users are project managers, GPS managers, estimators, and surveyors for construction companies. The digital twin is visualized with a Cesium JS viewer, which forms the core of the application's front end. Users can overlay data from various data sources, including design and CAD files, point clouds, and digital terrain models derived from drone flights, and machine as-built data from Komatsu Intelligent Machinery, and machinery from any other company if you use our Komatsu's retrofit kits. One of the benefits that using a Cesium viewer provides over a typical GIS is that the site is accurately geo-referenced on the globe, and users are given the full surrounding site context via the Cesium world terrain. So users typically fly drones on a weekly basis, and machine as-built data is uploaded directly to dashboard projects on a daily basis. These surface layers are organized in chronological order in dashboard, and progress can be visualized in a variety of ways, including heat maps within the Cesium viewer and a variety of timelines, charts, and tables. Dashboard also makes extensive use of the Cesium viewer for measurement calculation. So viewers can draw annotations directly in the Cesium 3D viewer, select design or surface layers to run the calculations on, and then see their results displayed in the Cesium viewer as a heat map. And the height maps that we use as the basis for these calculations are also generated from the 3D tiling pipeline that will be discussed later in this presentation. So that was just a quick overview of Dashboard. Next up, I'd like to welcome my colleague Sergio Nizama, who is going to discuss smart construction simulation.
Hello, I'm Sergio. I'm a software engineer at EARTHBRAIN, and I work on smart construction simulation. And that's what I'll be talking to you about today. So smart construction simulation, or just short for simulation, is an AI-powered tool to run simulations on earth-moving tasks in order to maximize production on a construction site. Yep. And an example of simulation running there and distributing soils between different areas of the construction site. So we use Cesium.js to visualize simulations that help effectively plan tasks and schedule those tasks, as well as manage construction machines and soil resources for the construction site. The app has like a step-by-step process to help you set up the simulation. As you see on the sidebar here, you have a site setup menu. And once you go in there, kind of similar to dashboard, you do upload survey data of the initial soil surface. And you also upload the target design of the final construction design. And along with that, you also need to specify an entrance point to the construction site and put aside some stockpiles of earth, soil. So after the initial setup of your site, then we move on to dividing up the entire construction site into different regions that we call work areas. Work areas are basically regions that are designated either as to be excavated or filled in order to meet the target design, basically. Sorry. So these work areas are automatically generated when the user opens the options for the first time. And they are generated by comparing the height differences between the source and the target design. And you're able to further optimize the work area by using AI. It optimizes it to make it a more efficient grouping of the work areas. In addition, besides just automating those divisions, you could also divide it by drawing a line or polygons, which will create a new area by those segments. And of course, you could also merge the areas by just selecting and then clicking on merge. And also, in addition, you could add structures such as road and barriers, which affects the simulation when it comes to soil distribution throughout the construction site. Another structure you could add to work areas are slopes. On a physical site, slopes are basically created by excavators compacting soil with the bottom of their buckets. And these are essentially an additional work process that has to be done. And slopes help identify surfaces that need compaction and basically also help you set up those tasks for your schedules, and also affects in setting volumes for the soil distribution. Afterwards, we divide the work areas, then we move on to simulating the soil distribution throughout the work area. We want to find the most efficient way to move around soil throughout the construction site so that we can minimize costs and be more efficient. It's smart enough to start a process, and then if it's more efficient to continue to another work area, it will do that back and forth to have the most optimal productive construction process. Okay, an additional feature that we have that we added recently was water flow predictions. These are basically, you provide the topographical data and how much rain you expected to receive. And then we run it through a simulation process that basically renders out Cesium primitive points. And then you can see here in some example on the left, those are puddle accumulations. On the right is the flow of the water flowing through the watersheds. And the bottom left is the different watersheds of the working area. And you can see the zooming in, and there's just all point primitives. And then we have this concept of machine groups. This is basically where you assign your construction machines to different tasks of your simulation. There's basically 3 different types. We have the soil distribution group, the cut group, and the fill group. And this is mainly so that as a user, you could kind of experiment with different types of configurations of machinery and quantity to see how your simulation will run, and budget, price, and things, money, and things like that. And then this is part one of the last steps of simulation, which is just scheduling. That's partly the main point of simulation is to be more efficient with the scheduling. Users can generate schedule based on average work and the machine capacity of the selected machine group. And that was a big, quick, brief explanation of SC simulation. And next, Chet will talk to you about data pipeline for SysMD. Thank you.
Hello. Good morning. My name is Chad. I am also a software developer at EARTHBRAIN. Today I will be talking about the 3D pipeline for the Cesium viewer. So before we start tiling anything or uploading any assets, we need a few things. One of it being a dashboard project, a site CRS pertaining to the site area we want to upload the assets to, and some assets. So we will go through that right now. So some of the assets that we process at EARTHBRAIN is 3D surveys, which is around drone data, machine data, satellite data, 2D images like ortho photos, so satellite data, photographs, and design data, which is buildings, software like AutoCAD, and line work. Here's an example of one of our data types we take in. So for surveys, we take in point clouds, like CSVs, text, and we also take mesh data, like DTM, DSM, which is the 3D satellite data, XMLs, and DXF. So let's go through the settings necessary to upload a CSV. So let's say we want a survey data, and we require some information from the CSV, like the point formation, which is like the XYZ location, and maybe some colors of that point, which is the point formation. And depending on the asset and what area the site is pertained, the distance units can be set in meters, US feet, or feet. All this is relatively used for projecting the points into the site location and onto the viewer. So we also have advanced tiling settings that does extra processing within the tiling process. The most interesting one for me is interpolation. I won't go into the detail of interpolation, but if you know, it's just adding points to gaps that are where points does not exist. Let's go through the workflow. Going from left and right, in the beginning, once we get all the information, we start to go within the tiling data pipeline, which we kind of actually store all of our tiling binaries, or written in C++. And we also get the GIS repository, which is the project data used for storing the CIS data. And then we start a conversion process. Pretty much the conversion process to process any units from feet to meters. And then we will create the executable commands, which is basically the binary and the settings required to tile the asset. And then we start a tiling job, which is then passed to our servers, and then we run the tiler. Let's get to it. So here's the meat and potatoes of the tiling process. Basically, you start from the projection of the given option, and we pretty much parse the projection from the site, and then we convert the points from the data, and then we pretty much get a bunch of chunks of data, and we organize that chunk. And then we create what we call a AABB, which is a box in memory within the location coordinate system. And then we would then also calculate the transformation that the tileset needs to write the tileset later. So we're doing two things at once at that time. Within the ABBB, we create an octatree, which is a tree that will store all of our tileset data, or points data, and then we read the points in the asset, and then we transform those points to the local projection, and then we store all those things in the octatree. Don't worry, there will be an image later on that will explain that. It's very confusing. We also do extra processing for, like, example, interpolation. We will add points into the octatree in the middle before writing the actual point into the tile set and making our point data. Here's an illustration of the octatree. The top you can see is the purple square that can be represented as ABB, and the 8 points is each different quadrant of that square, and then you can see that there's points within that square that can be represented as the point data. Right after writing the point data, we do some extra processing, like we generate height maps for measurements. We convert files. For example, some files can be started as CSV and then CSV, and then we can export it as XMLs and different file types. And we can also create point clouds and create mesh out of them. So creating the 10 files so the users can view it in either point or mesh. Lastly, we take those tiles.json, we save them, and any extra processed files, we also store in our data storage. We serve the tiles.json and points from our servers. So, and then from there, we are able to extract those point data and then render on a Cesium viewer. So at the moment, from my previous colleagues, dashboard and simulation currently uses this process. I think this is Design 3D also. And that's the end for mine. Thank you very much.
So hello, I'm Ryoji Shimizu from the EARTHBRAIN, software engineer. So I introduced the 3D model placement library. So first, why we created this library? So we want to realize the construction site in a digital space. To do this, we need to visualize and control things like construction machines and the materials are in a 3D Cesium environment. And then our challenges are, so how can we prepare 3D models on the web efficiency? And then how can we present key features with good developer experience and then easily extend any Cesium.js application? So to solve this, we choose two main strategies. So first, use the GLTF model for 3D models, and then because the GLTF is the lightweight and good compression and good quality by PBL. So, and second is the library approach, and instead of integrating the directories each into the application, so we designed the general purpose API and then scalable development environment using Beat and monorepo structure. So as a result, we developed our library with built-in construction machine models, and then it's already used in our production development. So let's now look at the key features. First is the built-in GLTF model. We including the 15 construction machine models applying with the realistic size. So they can be replaced correctly in the scene. So like below bottom of the image, as we can see in the bottom image. And then, so next is the intuitive control machine interaction. This is the using our API, and you can control the models and your mouse on the viewer and height change and rotation. So in the real time, and and then also this in the gizmos, less sphere and the yellow block, and then dot line is also Cesium entities. Thank you for creating these very good development experience. And then, so next is automatic terrain placement. Is if the mouse hovers out, the clamping the surface directly automatically surface detection. So and then finally the collision detection. So construction site is the need for the safety, and then so we can see visualizing the what is the danger or safer, and the green is the safe, and then red is the danger. And so real-time collision detection, and then we can see the for the safety construction site. So finally, next action. So we want to improve the library so it can be used more widely. Here we have feature goals, support more 3D formats, and a more detailed operation, like showing how the excavator moves, like see images, and improves hazard assessment features, such as adding overweight and slope limitation. That's it. Thank you.